Okay, so now we're going to study EM waves in conductors. And eventually we want to arrive at perfect electric conductor, which has the perfect property for electrical field. So first of all, for any conductor, we have Ohm's law. So we want current, so we need to push on charge to form current. So Ohm's law tells us that how good a conductor is. So we have the current density. So this is free current equal to conductivity, and then field, which is force per unit charge. So if we have really perfect electric conductor, we will have the conductivity equal to infinite. And next we have Maxwell's equations. I'm going to use this opportunity to summarize both the integral and differential forms of all the Maxwell equations, and hope that this would jog your memory. Okay, so first we have Gauss' law. We learned Gauss' law from integral form first, which is the closed surface integral on the E field. This equals to the total charge enclosed. And now in any material, it is free charge enclosed divided by the permittivity of that material. So this is what we learned at the beginning, the integral form. But actually, what we learned at the beginning was, free space, but this is very easily extended to any material. And then we have, if we call the fundamental theorem for divergence, we have the volume integral divergence of E d tau. So this equals to here the total charge. So we use the volume charge density to match the volume integral on the left hand side. So I have the volume charge density, free charge density for any material, and d tau divided by permittivity. So now we have the volume integral on both sides. We can take out the differential form for Gauss' law, which is the divergence of E equals to free charge density divided by epsilon. And second, we have the closed surface integral of B field. What is this equal to? So we should have this equal to 0 because there's no magnetic charge whenever, wherever. So here for E field, we have the free charge enclosed, but for the B field, there's no magnetic charge enclosed anywhere. So if we call the fundamental theorem for divergence for this one, we would have, eventually, let's write it out anyway. So I have the volume integral divergence d tau equal to 0. So the differential form, we have divergence of B field equal to 0 anywhere, and whenever and wherever, it will always be 0. And third, we have Faraday's law. So we have the closed loop path line integral of the electrical field. This equals to the change in magnetic flux. So we have dt, and then surface integral B dA. So now if we call the fundamental theorem for curl, on the left hand side we have the surface integral curl of E dA. So now we have the surface integral on both sides. We would have the differential form, which is the curl of E equals to minus dB dt. So this is partial derivative because we did put b inside of the the surface integral. So b can be a function of x, y, and also t. Okay, the last one. We have Ampere's law, and we also have Maxwell's correction. So this tells us that the closed line integral of the B field, this equals to, Ampere's law tells us this equals to the total mu and then total free current enclosed. And then the Maxwell's modification tells us that the flux of E field, the change in E field, would generate magnetic field. So we have plus mu epsilon d dt, and then surface integral E dA. So here we call the fundamental theorem for curl on B. So we have the surface integral curl of B dA. Here we have surface integral, so here we have mu surface integral the volume current density dA. So let me finish this equation anyway. So we have mu epsilon d dt, and then surface integral E dA. So this is confusing. This could be a confusing point here. So why this is volume current density, but we only do surface integral? But what I had before was for the volume charge density, we do volume integral. This is because current here equals to line current density. And then when we actually calculate the B field based on Biot-Savart law, we need to do another line integral here for the current line density. So here from 3D current volume current density, we only need to do 2D integral to get the 1D line current density. And then when we actually calculate the B field based on Biot-Savart law, there is another line integral. So altogether there will be 3D. So I hope that's helpful. And then we have the differential form, which is the curl of B equals to mu J, the volume current density, plus mu epsilon and then dE dt. Okay, so now we have Maxwell's equations. I hope when we study physics, when you are given a piece of paper, you should be able to write equations down on the piece of paper by yourself. So electromagnetism is very challenging because a lot of concepts are connected. And also when we apply these mathematical rules to different scenarios, there are a lot of simplifications on the conditions, so that can be very confusing. But we can always come back to the original definition of all of these. which is agreed by everyone. Okay, so another important addition to Maxwell's equations is continuity equation. So I have the divergence of the current density equals minus d, the volume charge density, dt. So how much current flowing out from a point equal to the speed of charge losing. So how much charge is losing over time at that point. So this is really important addition to Maxwell's equation. So now if we apply Ohm's law to this, so we call Ohm's law to here, we have rho C, and then divergence of E equals to minus d rho F dt, free charge density. And now we call Gauss law here. We know the divergence of E, so we call Gauss law. We would have the conductivity divided by permittivity, and then rho F equals to minus d rho F dt. So this term is determined by material. It should be a constant. And then it is very clear to see that the charge density should be a function of t. So charge density is a function of time. So the solution of this differential function, we have rho F as a function is a function of time equals to t minus the conductivity divided by permittivity multiplied time, and then there is an initial constant term. So this means that we have an initial free charge which is rho F 0, and then we'll be losing charge over time. So we have a parameter that's called characteristic time. Tau would equal to epsilon divided by sigma c. So after this time, the volume charge density would be lost by a factor of 1 divided by E. So this is a good indicator of how fast charge density is lost. Now, if we really have a perfect electric conductor, we will have conductivity equal to infinite, and then we have tau equal to 0, and then pretty soon we lose charge almost immediately. So we have rho F equal to 0. So remember what happens to the conductor when we have external electric field. So if it really is a perfect conductor, all the charges are free to move. So they will be moved by the external electric field to the surface. So the induced charge will try to cancel the electric field outside, so that the total electric field inside would equal to 0. So charge density, volume charge density inside would be 0. But their surface charge density. So the charge that resides on the surface, so we would have surface charge density. Not to confuse this with conductivity, so this is free charge density, surface charge density. So if there is a perfect electric field, then we have eventually we have the free charge density equal to 0 pretty much immediately. Okay, now we know that for perfect conductor, there will be no volume charge density. So here we don't have volume charge density anymore. So we need to modify Maxwell's equations for conductor. So let's do that here. So I have the divergence of E field. This equals to 0 because there's no volume charge density. And then we have the divergence of B always equal to 0. And then we have the curl of E equals minus dB dt. And then finally, we have the last one, we have curl of B. So here we have the current density, and we call the Ohm's law. We can put E field in here. So what we have is curl of B equals mu conductivity and then E field plus mu epsilon dE dt. And now we have Maxwell's equations for conductor. So can EM wave propagate in conductor? Any guesses? We'll prove that if it's perfect electric conductor, it's not possible. But anything that's less than perfect, there will still propagation, but it wouldn't have perfect propagation property. So anyway, so you remember in free space and linear medium, we try to prove that Maxwell's equation comply with wave equation. So we did that by doing curl of E field. We called a mathematical rule. So this equals to the gradient of divergence of E field minus Laplacian of E field. So now if we look at this mathematical rule, we still have the divergence here equal to 0. And then this thing here, we know the curl of E equal to dB dt, so we can apply curl on B. So this equals to minus d dt and then curl of B. And then we know curl of B equal to this. So if we extend this further, we get minus mu conductivity dE dt. And then plus, minus, so minus sign here, minus mu epsilon second derivative of E with respect to time. Okay, so if we organize this, what we have is Laplacian of E equals to mu epsilon here. So here we have minus sign, so here we have minus sign, they all become positive. We have second derivative of E with respect to time. And then we have extra term here, plus mu conductivity and then d E dt. So this is really extra for conductor because when it's dielectric or free space, we have conductivity equal to 0. And then similarly for B field, we would have Laplacian of B field equal to mu epsilon second derivative on B of B with respect to time. Plus a mu conductivity dB dt. So this doesn't comply with the wave equation anymore. So let's recall what was wave equation. Wave equation must comply with second derivative of the wave function with respect to distance equal to 1 divided by the velocity of wave. And then we multiply a second derivative of the wave function with respect to time. So when wave function f comply with this wave equation, we have the wave propagate with fixed shape, constant velocity. So initially in linear medium, and also free space, we have Laplacian of E equals mu epsilon second derivative of E with respect to time. And we also have the Laplacian of B equals to mu epsilon second derivative of B with respect to time. But now for conductor, we have second term. So this means when EM wave enter conductor, it wouldn't maintain fixed shape, constant velocity. So that's really special about conductor. So actually, in fact, what it means is that when wave enter conductor, obviously if it's perfect conductor, when wave enter the perfect conductor, there will be attenuation very quickly. So obviously, the wave wouldn't maintain the fixed shape, constant velocity. But we can still write wave functions for conductor. So I have modified wave functions. So suppose we still have plane wave where electric field, magnetic field, they polarized in the xy plane and then propagate in the z direction. So we have transverse. So E and B and the propagation direction, they are all perpendicular to each other. So we have E field equals to polarization, and then EI, and then we have kappa is a complex value now. The wave number is a complex value. That's very special about conductor. And then the rest is the same. Similarly, we have B field equals to the vector magnitude, and then EI kappa complex value kappa z minus omega t. Okay, so this is very special about conductor. So for these wave functions, we have kappa complex value kappa squared equal to mu omega multiply epsilon omega for the real part plus conductivity for the imaginary part. So here kappa, we have kappa real part plus I kappa imaginary part. So what does this mean? So first of all, if we have conductor, it doesn't have to be perfect conductor, but good conductor. We would have conductivity substantially bigger than epsilon omega, substantially bigger than this. So this term would be dominated by the imaginary part. Then the solution to this question, to this equation, we have kappa real part equals kappa imaginary part. This equals to omega conductivity and then mu divided by 2 and then square root of this whole thing. You can confirm this by checking, a plus a squared equals to 2i a squared. So you can check, you can put this back and check this. So we have real part and imaginary part. And now what happens to the propagation function here? So for propagation, we have ei complex valued kappa z minus omega t. So if we extend the complex k, express kappa by kappa real part and kappa imaginary part, we would have e minus kappa imaginary part z, and then e I kappa real part z minus omega t. So the imaginary part, there is a I multiply I, we have minus here. So this one is taken out, and this one is similar to the wave function that we always have for linear medium. So if we only have this term, wave would propagate with fixed shape and constant velocity. So what is this? This is attenuation. So we have attenuation, which is given by the imaginary part of kappa, determined by imaginary part of kappa. And based on this, we have a definition of skin depth. Where this skin depth equals to 1 divided by kappa imaginary part, which means after this distance for z, so after this distance, the attenuation would be e, so the amplitude will be reduced by a factor of 1 divided by e. So that's a very important indicator. So if we really have perfect conductor here, sigma will be infinite, and then kappa imaginary part will be infinite, and then skin depth will be 0. So electric field wouldn't enter conductor at all. The skin depth is 0. So that's a perfect conductor. And then, so the imaginary part would determine, the attenuation and would determine the parameter of skin depth. And what about the rest of periodic parameters that determine periodicity? So I have periodicity property that is still determined by here. So they are determined by the real part of kappa. So we have a range of parameters where wavelength would equal to 2 pi divided by the real part of kappa. that is a periodicity for in distance. And also we have the velocity equals to the angular frequency divided by the real part of kappa. So here omega equals to real part multiply the speed of wave propagation. And then we also have index of refraction. This should equal to C divided by V, and the V is given by this. So we have C kappa real part divided by omega. So real part of kappa determines the periodicity property of the wave function, and the imaginary part of kappa determines attenuation. So one last property is, the relationship between B field and E field. We know that, in linear medium, we have B field equals to 1 divided by the velocity in that wave of that wave propagation, and then the propagation direction cross E field. We practice this quite a lot, so hope this become common sense to you now. And now for conductor, we would have B field equals to complex kappa divided by omega. So originally omega divided by kappa just give us velocity, but now we have the complex kappa, and then we have the propagation direction cross E. So these two, they can be derived from the third equation in Maxwell. So we did practice that for free space linear medium. So we are so familiar with that. We don't. So for linear medium, we did do here the third equation. We did the curl of E, and then we did dB dt, and then match x and y components of both of E field and B field. So the same can be done for conductor, and this is a conclusion which is quite easy to remember anyway. Okay, so now we already know that electric field wouldn't penetrate a perfect conductor from Ohm's law, and also from continuity equation, and we also confirm this based on the wave function. We know that the attenuation here would be really large, that the E field, it wouldn't just penetrate the conductor. So now we are going to prove this based on wave functions. So we are going to calculate, assume there is incident wave, there is reflection, there is transmission. We already know the answer that the transmission would be 0 for the E field. Now we're going to prove this. This is going to be very simple compared to linear media. So, and we also already know the conclusion anyway. But this process will demonstrate something new as well. So it's very important that you derive all of this as well. Okay, so suppose we have a linear medium on one side. It could be free space as well. So that would be this would be kappa 1. It's real valued wave number. And then on the other side we have conductor, which has complex valued kappa 2. So now suppose we have incident wave, reflected wave, and the transmitted wave. So we are still going to do normal incidence. That's already sufficient for us to prove our conclusion. So first, let's write out the incident wave function. So for the incidence, we have EI equals to E0. Suppose the incident wave is polarized in the x direction. That would make everything simpler, and the propagation direction is perpendicular to the surface, so normal incidence. So we have the propagation function I kappa 1 z minus omega t. Polarization direction is x direction. So we have the magnetic field here equals to 1 divided by V1, and then propagation direction cross E field. So we have 1 divided by V1, and then the same propagation function I kappa 1 z minus omega t, and then the B field is the direction is y direction. So z direction cross x direction and give us y direction. So that's the incident wave. And then reflection. We have ER, and we still use a ratio R to indicate, how much wave is reflected. And then we have the reflected wave propagate in the minus z direction. So we have I minus kappa 1 z minus omega t. Polarization is still x direction. And then we have the B field. So this is equal to 1 divided by V1. And then the propagation direction is minus z. So minus z cross E field. We have ER here. I forgot to indicate here we have EI. Okay. So this would equal to minus R divided by V1, and then E0, and then EI. So I have E. That's still quite ugly. So I'll just write it here. So minus R divided by V1, and then EI. The same propagation function like this, minus kappa 1 z minus omega t, and then y direction. So minus y direction. So I have here minus y direction. I forgot something here. We also have E0. Okay, sorry about that. So we have transmission. So ET is, we have the amplitude ratio T, E0, and then EI. Now we have complex valued kappa 2 z minus omega t. Polarization is still x direction. And then we have BT equals to complex valued kappa 2 divided by omega, and then the propagation direction cross ET. Forgot something here. This is direction. So this equals to complex valued kappa 2 divided by omega, and then T, E, 0, and then E, I, kappa 2 complex valued Z minus omega T. So direction is still Y. Okay, so I have three set of wave functions, which is not very hard. And then we have boundary conditions. We need to make these three waves meet as a boundary so that we can establish relationship between them. So I have boundary conditions. So for the full boundary condition, universally true, we have first, we have epsilon 1, E1 normal component minus epsilon 2, E2 normal component equal to the surface charge density. So this is given to us by Gauss law. So on both sides, the E field will be different, but they share the same free charge on the surface. So when we do surface integral, we get the normal component of the field. And then secondly, we have B1 normal component minus B2 normal component equal to 0. So there is B1, B2, they are on both sides. They don't share any magnetic charge. There is no magnetic charge to share. And then third, we have E1 parallel component minus E2 parallel component equal to 0. So this is given to us by applying Faraday's law. So E1 and E2, they are on two sides, and there is a flux. So we do the closed line integral, and that line integral wouldn't close anything because Faraday's law give us flux of the B field, and the flux over infinitesimally small area would give us 0. So we have parallel component equal to 0. And then finally, we have 1 divided by mu1 B1 parallel component minus 1 divided by mu2 B2 parallel component. This equals to the free current density cross the normal direction to the surface. So this is given to us by Ampere's law. So when we do the closed line integral, we have the current enclosed. And then there is also Maxwell's extension, but that gives us flux, electric flux. And electric flux over an infinitesimally small area give us nothing for the parallel component. Okay, so now we are ready to establish relationship between them. So first, the orthogonal component. So from here, for this polarization, we have x direction, x direction polarized for the E field. So all the E field, they have x direction. All the B field, they have y direction. They are all parallel to the surface. They don't have normal component to the surface. This is also because we apply Maxwell's equations that require the wave to be transverse, where the E field and the B field, the direction of them are perpendicular to the direction of propagation. So we know here we are investigating normal incidence, so the propagation direction is perpendicular to the surface. Then for the fields, they don't have normal components. So from 1 and 2, we have E1 normal component at z equal to 0, so at the surface, location is variable z equal to 0, equals to E2 normal component at z equal to 0. And we have B1 normal component at z equal to 0 equals to B1 normal component z equal to 0. And this equal to this also means so the E field normal components are all 0. So these two are all 0. This also means that the free charge density is 0. There's no free charge density, there will be no free current as well. So these two are going to be useful for later for the other boundary conditions. So now the parallel component for the third boundary condition, we have parallel component for the electric field on the left equals to parallel component on the right. So we should have EI plus ER, this at z equal to 0 should equal to ET at z equal to 0. So now if we look at all the electric field, so when z equal to 0, these are all 0, and then omega t, they are the same for all of them, so they get cancelled. And then E0 is the same for all of them. So this boundary condition gives us a very simple relationship between R and T, which is 1 plus R equals T. So I have 1 plus R equals T. And now the third, the last boundary condition, we have 1 divided by mu1 B1. So let's say BI plus 1 divided by mu1 BR at boundary equal to 1 divided by mu2 BT as the boundary. So let's look at all the magnetic field. So when we have z equal to 0, these propagation functions, they can be cancelled because omega t, they're all equal to each other anyway. So E0, here I also forget E0 term in here. So E0 is also cancelled. E0 is also cancelled. So this relationship on the left will have 1 divided by V1 minus R divided by V1. And then on the right, we'll have kappa 2 divided by omega multiplied T. So this gives us 1 divided by mu1 V1, and then 1 plus R. Sorry, 1 minus R. So 1 minus R. So this equal to 1, no, that's equal to R, sorry, here, kappa 2 divided by mu2 omega T. So this is another relationship. So based on these two, we would have expression for R and T. So if we define, so based on here, if we define beta, complex beta equals to mu1 V1 divided by mu2 omega, and then multiply kappa 2. Then here we have 1 minus R equals to beta T, and here we have 1 plus R equals to T. So this would give us R equals -1 and T equals 2 divided by 1 plus complex beta. Oh, sorry. Oh, gosh, so tired. Got it wrong again. So here we have, so if we put beta here, we have 1 plus R equals T, and here we have 1 minus R divided by beta equals to T. Yes, equals 1 minus R divided by beta. So this gives us R equals 1 minus beta. Let me just write here. R equals 1 minus beta divided by 1 plus beta. And then T equals to 2 divided by 1 plus beta. Okay, so you can confirm based on this, and you have 1 plus R equal to T, that gives you T. Now, what happens when you have perfect electric conductor? We have so if I have perfect conductor, the conductivity is infinite, and then kappa would real part, imaginary part will both be infinite. And then when kappa is infinite, beta is infinite. So when beta is infinite, we have T equal to 0. How good is that? And then R equals -1 because 1 divided by beta -1, and then 1 divided by beta +1. So we have, PEC would have R equals -1, and then T equals 0. We have total reflection. So total reflection, the wave wouldn't penetrate the conductor. One thing to be careful about here, we must be very careful. So when we have PEC, the wave is completely reflected, which means that R here is -1. So basically we have, for the electrical field, we have electrical field on the left, Z equal to 0, equals to electrical field on the right, Z equal to 0, just equal to 0. So I have the incident electrical field, reflected electrical field, and then at the boundary, Z equal to 0, they are opposite to each other because R equals -1. So the total electrical field on the left is 0, and then total electrical field on the right naturally is 0 because electrical field doesn't penetrate perfect conductor. So careful, this is perfect conductor. However, for B field, so here on the left hand side we have B field here, E0 divided by V1. On the right hand side, R is -1. Here I have minus sign, so I have E0 divided by V1 again. So at Z0, variable Z equal to 0, what do I have for the magnetic field? We have on the left magnetic field, would equal to here E0 divided by V1, and then here E0 divided by V1 again, because R equals -1. So I have 2 E0 divided by V1, and then EI omega t minus omega t y direction. So there's magnetic field. This is another special case. You know, at the beginning, when we introduce perfect conductor, when I first introduced Ohm's law a few lectures back, I asked, there is a past exam question, is it possible that we have, you know, current but we don't have electric field? It is possible, because for perfect conductor, we have the conductivity equal to infinite. So even if we have value here, we divide this by this, then electric field equal to 0. So okay, that's all the knowledge of my part of teaching. Yeah, I hope you have enjoyed it, and I hope this set of videos, they really help you. Thank you for your attention. Thank you for following all these videos.